So what I'm going to do today, hopefully you all received my little itinerary I sent you earlier, and I'm just going to load up a typical frame, and we'll go with this frame and get new. Now, what I want to look at is a quick recap, first of all, on the viewing tools that you have in the MasterSeries. So I just turn off my member numbers and my node dots. The zooming and panning is very easy. That's very straightforward. We use the roller on the mouse to roll in and out. Obviously, with this streaming live to you, you may not see every single change in the screen when I do these fast zooms and pans. So using your roller, you can zoom. Using your middle mouse button and the shift, you can pan. So hold your shift key down, I can then move my frame about. And with the 2010 version, it zooms now at the point you're looking at. So if I point to this corner, it zooms from there. So that's very, very simple. Now the next thing to understand is that we use two different graphics engines. And I'll just put this back into full front view. We use this advanced DirectX graphics, which gives us the speed that we require. And that should normally always be turned on. Now, when we've that turned on, if we look at our section sizes, we'll see just plain pale white shading of our sections. If we turn the next button on, we get different colors for different types of sections. And in fact, we get grey members for our concrete, we get green for any steel members. If we had composite members, they would be yellow. Timber would be brown. We can see here some plate girders, some plates, flats, they are coming in as a pale blue. And we can take that one stage further by asking to colour it according to sections. So we can see that these two sections are the same colour. And we can see these two are the same colour. And these two are the same colour, so they are the same section size. So the colouring is quite useful for seeing quickly, without having to read all the different bits and pieces. You know, if I turned on my section names, it can get quite congested. And just by looking at the colours, you can see the different colours and see where members should be possibly the same size. We can also throw up a legend to make our life easier, and because I've got this 3D color according to section turned on, I now have this legend available to me, and I can just zoom and pan, and there's my legend. It's quite wide because of this big plate description for my plate girder. Now the next thing I can do to make my life easier, I find, is to cut members back from their nodes, so you know what's a member continuing past the node, and that's something that's available if you've got MasterCAD. So if I have MasterCAD, I can cut back and I can see where my distinct members are. I can see that I've got something called a super member along here and a super member along here, and that can be useful if you've got the MasterCAD component. And I only show that just because people don't really know about it and don't make use of it if they have the MasterCAD, which is our application for doing drawings. The next thing I want to look at in these viewing is the zooming down and filtering of views. If I wanted to zoom on part of the frame, I can do so. But that's what we call a hard view zoom. It is actually a filter. And if I take these buttons, I can go back out to full view, I can return to my zoom, I can look at the zoom with my peripheral members attached, or back out to full view. And that's more aggressive than just the normal zooming in and out with the roller of the mouse, because when you do the other zooming, that aggressive zooming, those members are no longer available for copying or pasting or anything like that. And of course, we can also use these filters to set what we want to see. So I could say, show me only horizontal members. That's quite useful. Or only inclined members. That's very, very useful. And I could say, give me only, and use a multiple selector, horizontal and inclined. And that can be useful to you. Now, the next thing I want to look at is taking this filtering and zooming a stage further. And we do that using the member viewing groups. I know Martin covered these, I think, in the first phase of our little webinar. But I just want to quickly, and in the editor, look at the viewing. We have two groups. We have member and we have nodal viewing groups. So member groups, and we can see we have, if I turn off 3D, we can see we have these members in a viewing group. And if I turn off that, so it's just those members in one called portal. So I'm able to select those four members without showing this internal member, which I couldn't do. And I've got one called bracing and one called beams. So if I was to come back to 3D and I was to close this down, and now we introduce this pop-up side menu, the viewing options menu. So if I now go to viewing options, I could say, show me member viewing groups, and say only the portal. And I have to turn on the parent as well. So there I go, only the portal. Or I could say portal and bracing by saying multiple select, so I could say portal and bracing together. Or I could do the opposite and say hide the portal and the bracing. So I could hide my bracing in my frame for some sort of diagram output. And that's very, very useful. Now it's interesting also to note that I can have a member in more than one group as well. These viewing groups, you can have a member in more than one. And we have the same thing for our nodal groups. And the nodal groups, I will just quickly look at the viewing nodal groups, because we will use those in a wee while. I have two nodal groups. One is all my perimeter outside nodes, and the second one is some super member nodes. And I could create a third one, and we call it Fred. And I could say I want those, and I just say apply mode, and I'm going to have that and that node and that node and that node and that node, which means that these nodes are in this group, but that one and those outside ones are also in different other groups. So you can have a member or a node in several of these viewing groups, not to be confused with design groups, which are something that you use in the model manager, which we won't be covering today. So I just save that. And the last thing I want to look at in the viewing tools, well, there's two last things actually, is first of all changing your font size. If I just put these down as node points, I can come along and I can say give me my fonts at 8 point, and I can say give me my fonts using a different style if I really want to. So I could go for bold oblique and say OK. So there's my bold oblique, but that's not very nice for you to see. It's a wee bit and it takes you back to the typical. So I'm going to go for 9mm Tahoma, a nice clear option. And then we have the option to change color schemes. If you think about our 3D members, if we change our color schemes, we can change some of these settings so that they're now using a different set of colors. And there are several of them set up there, and you could even go into the customization at the front of the MasterSeries and define your own grouping. And this is a nice sort of soft pastel series of groups, or in my case I have a more primary set that I like to use in this system. So that's your basic moving around, looking at your frame. Different techniques and tools for viewing the frame. And I'm just going to take it back down and let's work on the basics now. So now we've dealt with our frame, let's look at the second facility, supports. Supports are what we call nodal restraints. So we have static supports. So first of all, we get introduced to something horrendous, not your normal icon you would expect, but something different. I'll explain that in a minute. So what do I have? I have 5 different groups of static support. So just highlight that a second. So over here it tells me it's 1 of 5, and this is the definition for this current one. And if I just go back to normal and we look through the different supports, so something pretty straightforward is a pinned base. I can make that a fixed base, or I can make it a roller, or I can make it something different. I'll keep it as pinned. And then we look at the more detailed ones. These horizontal restraints are just put in here on these nodes because we actually have some out of plane forces on these members. So we just put in a DZ restraint. So what do the 3 squares mean? The 3 squares are your X, your Y, and your Z in your directional methods. So we have a restraint on the Z, the third one. So where it's not one of the primary pinned or fixed or rollers, we get these little either 6 or 3 squares icon. And coming back up, we then have this one, which is a DX and a DZ. So it's got no vertical support, but it's got a torsional restraint onto the column. And then we have something that has, it's fully fixed except for, again, the vertical restraint. And there is a reason behind not putting these vertical restraints into these foundations. So that's our basic static supports. Now, why did we leave out some of the values? Well, we left out some of the values so that we can introduce springs. So over here, we've got a spring which is a 10,000 kilonewtons per meter vertical stiffness. Yes, it's a telephone number. So to get that to work, we have to leave out its vertical static support. Otherwise, it would be static. And we also have a small spring stiffness of 1,000 kilonewton meters per radian, and there's what 6 and a bit radians in a circle, so it's about 60 odd degrees will rotate you by 1,000 kilonewton meters would rotate you. So that's our springs defined. And the last thing I want to define are supports, settlements. So what I'm saying here is that I've got a settlement that is coming down by 10 millimeters. But in this case, we're going to introduce something additional, and that is that we're actually going to assign that to the N1 load group, because we've got a second definition that's got an N2 in it, which is 100 millimeters. So in any loading case where N1 is active, we will have a 10 millimeter settlement, and in any loading case where N2 is active, we will have a 100 millimeter settlement. So that covers your main supports, your static supports, your spring supports, and your settlements. But on the nodes we then have this fourth item, our loading. So we can apply nodal loading, very straightforward, 100 kilonewtons applied horizontally to these 3 nodes and in the W1 load group. We all are familiar with our W and our L and our N and our D load groups. We covered those all in the part 2 of this webinar. I've introduced a second set of nodal loading, but this time I inputted at an angle to the horizontal and vertical. So I've been able to say that I have 100 kilonewtons, which is applied at 45 degrees, which is going to get us, in fact, 70 kilonewtons horizontal and 70 kilonewtons vertical as our resolved forces. So that is activated by turning on this little button. So 100 kilonewtons horizontal, or in my case 100 at 45. And I could also go for a horizontal rotation to pull it out of the plane frame orientation if I wanted to. And we can do the same with our moments and their rotations, which would be quite fun. It's not something I recommend. So that is our support conditions. We've dealt with those quite clearly. The next thing I want to look at is member fixities. So member fixities, we can come along and we can do a member release, a member end release. And what we're saying here is that a member is pinned or fixed, or in these cases something different. So if we look at the releases we have for a pin, we can release it torsion, which means it rotates about its own axis. We can release it minor, so it bends about its minor axis, or we can release it major, bends about its major axis. So if we wanted to make this, let me see, this pinned here, this beam, it's pinned at this end because it's got all three released. If I decided just to release the major, which would be sufficient on this frame, then we can see we only have the last degree of freedom released. But since it won't really matter, we can release all 3 degrees of freedom, and it'll be then simply supported. And we can take those and we can copy them. So we can say, give me, for example, this member, and I want to copy the end release, and I want to copy it to that member. Sorry, master member is this one, I apologize, and then copy it to that one and maybe a couple of others, and I say proceed, and it does that as well. So we can quickly copy these definitions for you. And I go back to release near member. Then one of the more interesting facilities is this option here to release super ends only. So if I turn that off, I could put a support or a release in here and here. But if I turn that on, because this is a super member, which we will look at in a moment, I can only release the ends. So I cannot release here. So putting that back to being fully released on both ends. We've also pinned this member at the top and bottom, and pinned this one just at the bottom, because this is our portal frame. So those are your member end releases, pinned or fixed, and the default is rigidly connected. Now we also have the ability to actually go further and make these partially fixed, and to do that we apply that as a loading to the member. So what we do is we leave the member fully fixed, and then in the loading we introduce this part fixity here. So we're telling it this member at either end of the member has got a 20% fixity on the member. It's not pinned and it's not 100%, i.e. fully fixed. It's in between, it's 20%. And we can also stipulate which end is released at. So if I only wanted it at one end, I go minus minus, and then the release is on the left end only. And I can even say for a 3D frame what axis. Normally in a plane frame it's not a problem, we just leave it as being plus plus plus. But if we wanted to be more exact and only release it in its major axis, we could go minus 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 minus, because the MZ local to the member is releasing the local axis of that member. So if I turn on my 3D, you see the Z is into the page. So by holding on or releasing that z-axis, we affect the major axis of the member. But on plane frames, it doesn't really matter that much. You just do them all. We do the same technology to foundations to get partially fixed bases, but we've got to do two stages. We have to have the base fixed and then the release. So if I was to come down to, I think, one of these, here we go. At the bottom only, we've got this 20% fixity in all loading cases. And down here we have none. So I could turn around and put in a second one and say that when I have N2, I've got 20% fixity, and when I have N0, I have 0% fixity, so it's pinned. And I could say when I have N9, I have 99.99, which is in fact fully fixed inside the program. And then in different loading cases, I can activate these three load groups. And there's a very good document in our helps and tips on how to do that. So that if you're doing a portal frame, you could have it to be pinned under dead plus live, partially fixed under sway stability, and partially fixed under surface cases to get your deflections down with your 0, 10, 20 fixities that you would apply. So those are your member end releases. And now I want to quickly move on to our special loads. And our special loads are things like tension only. This is a bracing member, so it is tension only. So when we analyze, it will go into tension only. We can also do the same and put a member into compression only, so if there was an uplift, this would have no effect. On this frame that could be quite catastrophic, but it's something we can do. And most people will understand where you have a tension only member, but why a compression only? Well, it could be simulating a masonry column that you want to have no uplift in. There are one or two other ways of doing it as well. Now, the next thing I want to look at is something totally different. Free axial load. If you're thinking of a gable frame, sometimes you do a full portalization of that gable frame, but your gable posts, you then want to slide up and down so that the whole frame works as a proper portal. And you do that using the free axial load facility. It has limited use, but is something that some people use, so it's there. And coming back to this member, we also told it to ignore the self-weight. Now normally in a bracing scenario like this, you would consider the weight of the member, but you can ask it to ignore self-weight. It's used if you were doing a floor and you're trying to simulate a diaphragm action by putting in dummy bracing members of structural steelwork. You wouldn't want those weights to be included in the analysis, so you tell it to ignore those weights. And then getting on to the more analytical functions, we have something called lack of fit. Lack of fit is where you have a problem with construction. And I thought I'd put some lack of fit on somewhere. Obviously I haven't. So I'll put a lack of fit onto here. So if I say short in all loading cases by 100 millimeters, that's quite significant. It's going to try and pull this tower to the left and pull this frame to the right as the two tops of the nodes here are pulled closer together by a pretensioning of that frame. And we could do the same over here, and we could slip in another lack of fit. This time I'm going to put a plus to make it 100 mil longer than normal, so we can see the effect of variations in our member sizes. Stiff deck I will cover in a wee while, so I'm not going to cover that at the moment. But the two other ones I want to look at is thermal expansion. Thermal expansion we do in two stages. We define a coefficient of thermal expansion, which is normally 12 e to the minus 6. So unless you're in some obscure material rather than steel or concrete, just leave that value alone. And that would probably be a UT load group, since it's always going to be applied. And then we can tell it what the rise or fall is. So I can say, give me a rise in loading case N2, give me a 20-degree rise in this member. So 20-degree rise is going to cause that member to expand even more than we have with this 100 mil positive lack of fit rather than negative. So that's very, very useful. It's more useful when you're dealing with large buildings or large trusses where you want to heat up the top boom to see what effect that has on the frame. And finally, coming down through here, we also have live load reduction. If you're dealing in a multi-story frame, you are allowed to reduce the live load coming down. So 1 story, 2 story, 3 stories, 4, 5, 6, 7, 8, 9, 10, up to 10 stories at 40%, and above 10 you go to 50%. So that allows us, and what is the minimum height. We can also apply that incrementally at each level, which is probably not the norm. So we can apply this live load reduction, which is going to have very little effect on this frame, but in some design cases it is quite significant and is desired. So that's us sort of halfway through the presentation, and I'm nearly halfway through down my little sheet of features. What I now want to look at is supermembers. What are supermembers? Well, supermembers come into 3 different categories. If you think about this frame here, you've clearly got a beam across here, which in analysis is going to be one member. Since we made it pinned across here, that would make sense. But we input it as 2 separate components. But as you can see, members 5 to 6 are classed as one member. So we've glued that together at analysis time. And we do that from the super member menu. Okay, turn off the 3D. There's my super member 5 to 6. I could make that a super member across there if I wanted to, but I'm not going to do that at the moment because that has another job to do in a moment. So coming into apply mode, it's very simple to create a super member. You just pick them and glue them, and we'll see how we do this in a moment in one of the other facilities. If I go to design, I could make this a design super member, which is useful more in trusses than in multi-story type frames, because if you make this a design super member, it's going to design it from here, from this point all the way up to here as one effective length with no restraint at the mid portion. You could obviously in the design then put in that restraint if you so desired. The choices and flexibility is there for yourself. But the other powerful supermember is the drafting supermember. And if I remove all these just quickly, just by going cut, 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 I wanted to find some supermembers. So what I can do is I come along and I just say, well, from there to there it'll be one supermember, and from there to there's a supermember, and from there to there, and I'm going to go for from here to here and here to here. And what that means is 2 things. For drafting supermembers, they become a single member when we go into our MasterCAD to draw it out. So from an analysis point of view, who cares? But the second thing it does is it forces the properties to match, so that if this is a 203 23, this would have to be the same. Sorry, 46, 203, 203, 46. This would also have to be a 46 kg. So it's quite useful. And if I suddenly change this in design, this will automatically get changed in the design as well. So it glues their section size together, and that kind of makes sense, for you would probably want to bring these as one lift, or even the whole way up as one lift, because I could come to this super member and go for 3 legs. And that gives us great flexibility. Next, I want to look at cleaning up this frame. And what I mean by that is I've put some bugs into it, I've put some funnies into it, and I want to look at ways of cleaning it up. So first of all, if I look at my members, you will see that I've got 4 individual members here, plus I've got a member number here, which doesn't quite make sense. And here I've got 2 members crossing, which may or may not be happy for me. So this is a problem for me, because I appear to have an additional member in here that I want to get rid of. So where this is the model cleanup. So what we do first of all is we can pack unused nodes, and we just say proceed, and it automatically says, well, these 2 node members, these 2 nodes have the same location, so we'll make them the same number. And it's also done another thing for us. It's then said, well, this member no longer exists, so let's take it out. So that's very, very useful to pack. And I would recommend to people that they actually sort of, from time to time, if they're having a problem, or just for good practice, walk through the pack and the auto split. The auto split is thrown up one of these members, and the reason it's thrown up a member is very simple. If I come away from this, and this is why I didn't want to make these into super members, if I go to geometry and change nodes, take this node here, we should have seen that we only have 1 member number here, not member 10 and member 11, or member 10, 11, which would have told us that this is going from here all the way across. So I've got 1 member that's running from that node all the way to that node, and not touching this node here at all. So that is a problem. So just to go back to normal drawing. So going back to my geometry, my model cleanup, pack, auto split. The auto split will identify nodes that members run across but don't touch, and say, well, we should really split these. And it obviously gives you the option of whether to make it into a super member or not. So I'm going to say, yeah, keep it as a super member, and I'll say proceed. So now I got member 10 to 11, and this is connected to this member automatically. Again, a very useful cleanup tool. We also have the show and merge coincident nodes. And what we can do here is we can say show any nodes, and I'm just going to ask it here quickly, what's the length? This is 1.75 long. So I know it's a bit long, but if I say show me any coincident nodes that are more closer than a meter, there's nothing. But if I say 2 meters, it's going to say those are too close together and those are close together. So it's going to suggest that these are too close together, and I can say, well, yes, I better merge those. And if I wanted to merge them, all I need to do is say merge that node with that node. The with node's the one that remains. So I can then say show, and it would pull it across, which is what I don't want to do. And finally, you have in the cleanup the merge all, and the check for short members will tell you if it finds a member that's very short. Occasionally, coming in from DXF files, you can come up with those problems. And those are great little tools to find out your problems. So, that's your model cleanup. Hopefully we've got our frame okay. What I now want to look at is some analysis facilities that particularly in steel design you need to consider. So if I try to analyze this, will it work? And I need to put it as a space frame because I put some loads in the opposite direction. I have a problem with loads. So I could probably go back and fix that. But I'll not bother. But what I will do is put in my sway stability. Properties. Loads. Special loads. Notional load cases. Now, I at the minute have 6 cases, dead plus live, live only, and I have 4 win cases. And we saw 2 weeks ago how to create multiple cases, how to import cases. I want to look at the P delta and the sway stability. So first thing I'm going to say is, in this ultimate limit state first case, dead plus live, give me some horizontal notional loads. So find me and add 0.5%. Probably just find. It's probably cleaner, I find, to do it in the find. And then I'm going to tell it to give me 0 and 180 as my loads. I'm working to EC3 for my directions. So it's now gone up and given me 2 additional load cases. Dead plus live ultimate. And it's created those for me. The second thing I want to be able to do is P delta. Now normally you would not do P delta until after you'd analysed and attempted to design your frame, at which point you'd then do a check to see if your frame is sway sensitive and needs P delta. So let's just assume yes it does. So what are the different types? Non-linear, iterative is an old-fashioned iterative method. The geometric stiffness matrix method, as recommended in the SCI publications, is for multi-story type buildings. And because I've got bracing, I'm going to consider this to be multi-story building. The third method is the Newton-Raphson, which is really for rigid portalized type frames. So in this case I'll go for geometric stiffness matrix. I will say that I want it applied to all my ultimate cases, and I'll just say apply. So now I'm going to get geometric stiffness matrix method applied to all those. While I'm here, I can also, if I was a timber frame, select what my duration is for my timber members, and just leave that on as permanent. What other tools do we have in the analysis? Well, we have 2 additional ones. One is to ignore shear deflections. To include shear deflections. Very useful when you're doing timber or large concrete members. You would include shear deflections. And the other one is ignore torsional stiffness. And I will have to explain that using a different frame in a minute. So in the meantime, let's progress. And I'm not going to analyze this frame. I'm going to pull in a different frame that I've set up a whole multitude of errors in. So I'm going to go open. Yes, I'll save this. And I'm going to pull in a 3D frame with bugs. And now I have set up a whole series of problems in this frame. Hopefully I'll remember what they all are so that I'll be able to do them quite quickly. So we come along and we try to analyze our frame, and we get this message. Nodes 13, 12, 109 and 7 all have problems. We also might want to do an auto split on some members, and it says, I say OK. It now suggests that I should try and analyze it with a 1% fixity, and the answer to that question is yes, we should try that. And if that works, then we will examine our deflections using that. Now, you should never ever ever use that as a final state for your design. This is only an analysis tool. So having analyzed it with our 1% fixity, and just before I do anything, I have a lot of pinned members as we would expect. and that's why we get this 1% fixity. So into graphical and look at deflected shapes. So into deflected shapes, and we can see we've got big problems. So the first trick is to pull this back up to a small-ish magnification, and we can see that we appear to have a big problem around the back here, and we seem to have another problem here. Now what I always recommend is you put your frame in front view and you say, well, actually let's look at this one first and see what happened. Well, clearly something's moving without being attached to anything else, because you wouldn't expect this to be on its own out there. So I now use a slice to slice this up, and I then put it into the next side view, and in this case I can see that we have some sort of disconnection between these members, and you can see that this is trying to fall in. In fact, you can see here that this member is not even attached to this column or anything, so the whole thing is just collapsing. So it did mention an auto split, and that was probably the first thing I should have done. I just wanted to show you the problem. If you remember, Analyze, and it suggests auto split. So I say no, I come back into Edit, Geometry, and if I say Geometry, Model Cleanup, Auto Split, and it said yes, because we had members that crossed but didn't actually meet. So this beam was sitting not attached to these two members, and they had no node point. So I can say proceed. Now let's analyze again. We've still got errors, but we don't have the auto split suggestion, and I can say yes, and full frame again, output, graphical, deflections again, and we will see that we're getting a movement here. And the reason for this movement at a one-to-one deflection here is because we have got too many pins, so it's acting here as a catenary. So that I can fix, and I'll do so in the next cycle. We also still have this problem away around the back here. And anytime I see something doing this, I know that I probably have a support missing. And again, I'll come through and I will window to get a better idea of the frame, and I will look at the next direction, and I will then window again. So I'm cutting it up like a cake, and I can see, yes, we appear to have a total instability in this area. This beam's running all the way down, so it's got no support here. This column's just falling and hanging like a catenary. And if I put on my static supports, I would see, yes, I'm missing support there. So we'll go and fix those two problems. Edit, Restraints, Static, and we'll put a support there. And we also had a problem in the full frame, I think, if I remember rightly, with member releases. Yes, we had too many member releases there, so I'm going to go and say, and I take off this super member only option, otherwise I wouldn't get access to these. And I'm now going to analyze again. And we still have a problem. Node 7 has a theta x restraint. I say yes, again for the third time. Back in graphical, deflections. And looking at this, where is node 7 anyway? It's up around here. And this node is sitting on its own doing nothing. But the problem is that we have two full releases at either end. Now normally when you have bracing and the likes, if I turn off my node numbers, when you have a single member that's fully released on both ends, the program will automatically apply torsional restraint at one end to stabilize that member, so it's correct. But in this case, because it's got a node in the middle, it didn't see to do that, so that's totally unstable. That node's just going to spin around in space like a barrel. So I either need to get rid of the node or make one of these have a torsional restraint. So edit, and very quickly restraints, end release, and I'll just make that a normal without torsional release. Analyze again, and I analyzed. Now, strangely, when I was doing this earlier today and setting up this frame, I did get another error, which I don't appear to have at the moment, which is annoying me. Let me just see my conditions. Yes, and my supports. Yep. This column is on the verge of being unstable. All these columns are pinned, but the wee red vertical represents the fact that it's got a torsional restraint, so that we can't grab the column and rotate it around itself. Because if you think about it, fully pinned here, 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 and here, this column has nothing to stop it spinning on its axis like a barrel. So we normally apply this theta restraint, and in this case it hasn't fallen through that we should have it. So that is my analysis results. I've got my frame working and designed. Now the one thing I said I would come back to in here is the stiff deck. Now stiff deck is very clever. If we take even just one, put this in the front view, one floor of this frame, and you think about it, if it's got any horizontal movement, these are pinned connections because it's beam and post construction, and this is pinned and this is pinned, so there's no portalization of this frame. We're relying on the bracing zones here, 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 and over here, so 2 in the X and 2 in the Z axes. And this would actually just crumple like a big catenary with all these pins if we didn't say that the whole floor works as one. And that's what we mean by this stiff deck. And the stiff deck is a load that we can apply to each of the members. And if we look at a member, it's got a stiff deck. So it's got an MY, so it magnifies its own minor axis to make it work, so that these work as a solid slab. Now, the tip here is that it will not actually do that if the ends are pinned. So if this member here was pinned here and here in its minor axes, then the stiff deck would be useless, because it would still be pinned at all the supports. So what you normally do, if you remember in your static supports, is that they had only a major axis release, not a minor axis release, to make it work in stiff deck. So if we look at our stiff deck, we can see globally, turning off these, that we have stiff deck on all these members. And this is stiff deck only. If I go to single load, I can say give me stiff deck, and I can now see I have stiff deck applied to all these members. So all these members are going to act together in that floor. But that's not necessarily going to be correct, because as I said, that we really need to make sure that we still have, a minor axis. So I'm just going to say that I want to take these, and the correct restraint is this, where they're fixed torsionally and fixed in their minor. Sorry, I'm talking rubbish. Fixed in the minor. So it's only, my brain's not working today. Read it, Tommy, and you'll understand. I want to release only the major. I want it to be fixed in the minor and the torsion. So yes, I have, that's correct now. So most of them were correct with the 2 red dots, but not all of them. And that will now make that all work as one. So when I analyze and look at the output graphical and look at the deflection under a significant load, and we'll look at it for something if we have a bit of wind load, but we actually don't have any loads on it, so we won't actually see this, to be honest. It will all act as one, moving in one direction. If I was to come along, come back out quickly, which I'll do, and put a couple of point loads on just to make my point, edit. Always good to remind people how to put on loads. So nodal loading, and I'm going to put a nodal load here, 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 and here, and even there, and there, and there. And I'm going to put it in the z-axis. I'm going to make it 100. So we get these 100 kilonewton loads, and it will be the dead one, so it's always applied. So quickly analyze, output, graphical, deflected, shape. Obviously we're getting our vertical deflections as we would expect, but looking at it on plan, the whole frame has just moved in the z-axis, so we haven't got this big flexible type problem in our frame. It is working rigidly as if there's that slab holding it all together. So I've also covered here already looking at results, looking at my graphical results. You've obviously got, I want to come back and look at, say, bending moments on a frame. We covered this, I believe, in the previous, because we did look at our loading cases and load factors. And there's just 1 or 2 little areas I want to look at. If I was to say show the values, that's like a snowstorm. Obviously we can come along here and act smart and reduce our font. I'm going to go for 8mm, and it makes it clearer. I can also make it smart by saying only major axis. So if I zoom in, but I can also, had I had some member groups, I could have told it only to display the ones on those member groups. But at the moment I don't actually have that. At least I don't think I have. If I go to viewing and see if I have any member groups, I have no member groups, but I can do the same using, for labeling, I can say only draw my forces, multiple select on ones that have these section sizes. So just like member groups, I can elect which to draw it on, so I can actually put distinct values on an area. I should have had a member group set up, but you are probably getting this picture quite clearly. And if I turn on my section sizes, I might see what I'm talking about. No, it's not going to give them to me because I'm playing with this. And we're getting some more now onto our columns. So we can actually draw this and omit all the columns. You can also tell it to draw them but omit directions. So omit for labeling, only give me east-west. So now only getting my east-west moments at mid-span, which is quite clever, or north-south. So you could put out all your members there quite easily. So you can see these filtering tools are very, very useful. Deflections is something that people do struggle with from time to time, looking at the values of deflections. And I'm just going to come in here and look at an individual member, because this explains it in detail. So go to member diagrams, choose a member, this one, and maybe choose this one, that's better. Bending moment diagram, pretty traditional. Shear force, traditional. Minor axis, there's nothing. If you look at it, I have got two deflections. I have got the nodal deflection of the two nodes of 2.8 and 3.3 millimeters, and I have the overall deflection from here to here. So if you remember that value, 28.96. If I now come out of here and look at that member, just bringing my magnification up to something small, you'll actually see that it's given me a value of around 26. The reason is very simple. The 26 is the 28.9 less the 2.9. So when I look at the deflections in the whole frame, it's given me the relative displacement from the node points, which is what you want for your beam design. Okay, I've more or less covered everything I wanted to cover, except for the bit that says if time allows. There's two little areas I've left out. I will very quickly go through those. Output. We have our tabular output, which is very straightforward, but we also have internal forces. If you are working with some unusual material which we don't design for, spaghetti or something like that, you could ask it for the internal forces along a member, and you can say give it to me at 20 intervals between 2 meters and 4 meters. So from 2 to 4 meters I get my axial and my moment, my shear, my moment, and my axial, obviously maximum value. I can also say I want it at some distinct points, so give it to me at 1 semicolon 2. So it's intervals 1 semicolon 1 semicolon 2, which gives me 4 semicolon 0.5, and then obviously the start and end as well. So we can do all those fancy little facilities, and of course this can all be exported to your Excel or your Word documents if you have your calculation wizard. Martin, is the Excel only a calculation wizard function? It is. So if I have the calculation wizard, it will allow me, and if you excuse me a second, let's put it in the wrong page. If I pull it across, here we are. There we go. Internal forces come through as an Excel book. And save that. No, we won't save it. And don't save. So that's your member forces. Now, printing out is pretty straightforward to printers, but if you have a PDF writer installed, you can build up a whole booklet. And it's just worth noting how it works differently. So if I was to come along here and say print graphics, I can say I want to print to a PDF writer. So I've installed a PDF writer. PDF Creator I use is great. I think Martin uses something different. They're free to use PDF writers. Just Google them. So I've set it up as a PDF Creator and told it that it is a PDF document. And I now go print, and that's printed. So Nothing appears, no files, nothing, because it's now sitting inside the program as one page. If I now want to go to data and print data file, and I'll not mess around, I'll just go print, and I'll just say print. I've now got 7 pages in my repository, and I'll just close that. If I go back out to my graphical bending with values, and I just go print graphics, and just zoom that a wee bit till I'm happy, and say print. There we go. And close. It's now sent that to my repository. When I'm finished, or if I exit the MasterSeries, it will automatically close and produce the file. But if I want to close it now, I can close that and just say save wherever, and it will then open up my PDF file, and it's put that onto my other page. So here we go, the basic graphic, my data file, my properties, and then my little graphic, which I think I printed out twice. So that's the use of PDF documents. Now, ladies and gentlemen, it is now 1:05, and we've really finished. I think Martin will go through, has gone through most of the questions for you. I don't believe there's many left to answer. We will be providing all these as an email to you with all the answers, and we'll expand in any we feel we need to expand a bit more. In fact, Martin's written quite a little long letter on 1 or 2 of them. But the one thing I want to show you before I let you go is a customization. Because somebody asked, how do we change our colors? And that comes into the same category. And that is under File, Customization. We can stipulate where we want to start the MasterSeries. We can stipulate how we want to output things and whether we want a custom cursors to be used, absolutely. And we want shading and texturing, not that important. We can look at design codes, which one we want to start with, the BS or the Euro codes. And in masonry, which one to use. Our basic load factors to be considered. And we say, well, in Eurocode, if we say Eurocode, we should get the Eurocode factors, but we can change those up as we want. Now, but the more important things is coming into steel sections. I can do a couple of things. I can first of all tell it that I don't want to display anything but the EN 10,025 grades, and I want my default grade to be S275. I can also tell it that because I never use the European sections or the universal bearing piles, I don't want to display those in my drop lists, and I don't want the cheap cold formed sections to be displayed either, or the jumbo sections. I can also say, well, I don't want my 102 flanges. Well, maybe that one's okay because it's so small, but I certainly don't want the 305 by 102s or even the 127s to be displayed ever or used in auto design. So I can come in and I can configure that and customize it and then save that. I can also save it to a different drive. And if I go change drive, this allows me to take my sections database and shove it onto a central computer that everybody in the office uses the one set of section properties. Now, the other thing is editing the actual database. If we work with the default base, we can't do much. We can obviously hide some things, but if we choose an alternative database, we can then go in and edit the sections themselves. So into Open Library, and we can see our sections, and we can add sections. So if I have a historical section I want to add in, I can do that. Or if I'm based in India and I want to use the Indian sections, I can build up my database of sections and store them in here. And that's very, very useful. I'm not going to go through this. What I am going to do is I'm going to cheat. I'm just going to go straight into the user login area of the MasterSeries, and under technical notes you will find under MasterFrame some very good technical notes. There's your stiff deck we were talking about and your torsional stability we were talking about, and here is your open library sections, how to create one. We also have little ones here on the partial fixative, which we dealt with today. So these are all very useful, and the one we want is the open library sections, and it talks about how you do your open library sections, step 1 to 9, and away you go. So ladies, gentlemen, I have overstepped my time, but I felt that rather than run another webinar for 10 minutes, I would continue. So it only goes for me to say thank you very, very much for attending this webinar. There will